Thank you very much, Chairman. I came to India actually on Monday. It has been quite hectic for me to come here, but I managed it to come. And I'd like to thank Professor Sood for inviting me here to this wonderful event of Bangalore, India Nano. This is the first time to be. And I apologize the title of my talk because I realized this is rather application-oriented. So instead of giving this scientific talks, I decided to talk about something that's related to applications. Of course, I'm a physicist, so I like to talk about science. But of course, you can also see how this science concept can be extended to some applications. So here, my title is toward this wafer scale monocrystalline graphene. And I have two keywords. One is wafer, the other one is monocrystallinity of graphene. You rarely see this from other talks. So I can move on to, okay. So here you are talking about all applications and industrialization, which is very, very important for our life. But at some point, we have to think about, Korea has been leading industry in many different areas, like semiconductors, displays, cars. But now Korean government faces a question, what's next? And what can lead us to better richness? And in that sense, the Korean government start realize the basic science is very important. Because in order to create some disruptive technology that leads the whole world, you need something to think about, something creative. So government has launched a new program in Korea. So if you look at this, this number, it is the total amount of money for R&D in Korea, starting from 2.2% in 1995. Now 2013, it reaches 4.4%, which is almost twice of other OECD standards. So Korea has been quite serious. So when you consider applications, of course, it's important. But on the other hand, you have to consider even more future, what to next. For this, actually, Korean government launched a new program called IBS, Institute for Basic Science, to promote the basic science in Korea. Of course, the whole idea from the government is to create some kind of disruptive technology. But that can be, come later, okay? So with this, they actually tried to establish a research institute that focuses on basic science, similar to Max Planck Institute. So originally, they planned like 50 centers in the whole nation. But at the moment, we have 27 centers. The idea is give the money to the director, and the director can do whatever he wants. Of course, that will lead to eventually, to develop this disruptive technology. So I'm just one of them. I'm among 27 centers. And actually, 1/3 of the numbers of the directors is a foreign scientist. So you are welcome to participate in this program. And one of the specialties that is noticed by nature physics people is Korean university. We have only few number of government support universities. Majority is private, but still private universities supported by the company like Samsung. Our university, Sungkyunkwan University, is supported by Samsung financially. So this is why SKKU is growing these days. So one of the best universities in Korea. So our center now, our center was established in 2012, and we are focusing mostly on two-dimensional layered materials and try to explore some new physics and chemistry. For this, we have our own 7 tenure-track faculty, and about 30 postdocs, about 100 graduate students, and we have our separate new building. Of course, Professor Rao says building is not everything, but it does have something, so we need our space, okay? So this, this is the building provided by the university. And the total size of this, I mean, this one is composed of 3 buildings. One back, which is still empty. The one in front is ours, which is 9,000 meters square. It contains vibration-free TM, STM room, and dry room, clean room. So we are very happy. Of course, you know, we don't want to be limited by the blocks, okay? So inside this building, I'm sure when you visit us, you'll see we don't have compartment among you know, the different laboratory. This is completely one set of the building. It's a completely open space. Everyone can access to any system if they want, so we can share all this. So we still follow Professor Rao's speed. Yeah, and this one in front is actually brain science center. So we have 2 centers. We host one professor from foreign country, and he's leading this center. Okay, I mean, my interesting material is a 2D, and it is not just a new material. Even Feynman in late 50s, when he gave a general lecture on nano. Yeah, I think most of them you are familiar with. There's plenty of room at the bottom. But then he mentioned, I mean, if you read carefully, somewhere he says, what could he do with layer structures of materials with just a number of layers? So he already predicted there's something new if you consider, or if you control this, the layers. So nowadays we are focusing on many different type of materials. Of course, strongly motivated by the graphene, you know, tape science. So if you look at the table, we have a lot of choices. Of course, carbon, which represents this graphene. And just on the left and the right, we combine this boron and nitrogen. We have this completely insulating hexagonal boron nitride structure. And if you choose this chalcogen series and combine with transition metals, you can have many different materials with semiconducting or magnetic or even superconducting, any type of physical properties. So we have a bunch of freedom to play with. And these are the examples that one can imagine many different type of materials. And nowadays, in the laboratory, we can synthesize them in a large area, and there's no problem doing that. So the future is there, I hope. But since here the audience are mostly interested in applications, I like to focus on some topics that I have been working on, which is nanocarbon. Now, I think you are familiar with this fullerene, and people pay attention to this fullerene and did many interesting sciences. And following fullerene science, people are also working on carbon nanotubes. And of course, graphene is just another type of, you know, this sp2 type series. So basically, you know, we have freedom. You can either work with nanotubes or graphene and create whatever you want, like Professor Sanchez work with this inorganic, organic, you know, stuffs. So I'm not going to go through this one. Okay, so now if you look at and if you compare the properties of these carbon nanotubes and graphene, because they are basically sp2 type hybridization, their properties are very similar. Electrical properties, mechanical properties, thermal properties, they are very similar. Now then, why do we have to worry about the difference? But, you know, one is nanotube type, the other one is planar type. When you play with it, very different. Now, from my experience, nanotube, we've been working on quite a long time, and you know, even though it's a bottom-up technology, a lot of people have been working on, and we know how to deal with it. Graphene is less mature, I would say. So we still have a lot of things to do. So the first question, when people start with this Scotch tape, which is a small size, flake. And of course, as an industry people, oh, this is useless. Only good for scientists. So then people start thinking, well, how can we synthesize the large area? Of course, then you know, people started with silicon carbide, which is alternative silicon and carbon, and people simply try to anneal very high temperature, and you can see at the top of the surface, suddenly this graphene layer is formed. But silicon carbide is very expensive. People don't like that idea, and also, it's not so easy. Still, from industry point of view, this is not desirable. So people start working with some metal. Of course, this metal is a catalytic substrate, and if you supply hydrocarbon gases, you can simply crack them due to this catalytic effect, and then we can form this, some layers of graphene in large area. So, but when people use a nickel, because of the high carbon solubility in nickel, it wasn't easy to control a single layer, and then people come up with the idea that's copper, which has very low carbon solubility. And luckily, we are able to grow a single layer very nicely. Now, but still, sheet resistance or mobility is still not as high as theoretically expected. So people wonder what's going on. And one reason, of course, this is not single crystal, it's a polycrystal. So people try to absorb this synthesize this monocrystalline or single crystalline graphene. This is what we've been focusing on. So the idea of the CVD, chemical vapor deposition, is very simple. You have a substrate, which is a transition metal that acts as a catalytic decomposition of hydrocarbon gases. If you simply supply these hydrocarbon gases at relatively like 1,000 Celsius degree, you can decompose them easily, and you can deposit this on the substrate. So that's the idea. So when you imagine this one, of course, the nucleation seeds, it's not so easy to control. So they can start randomly from everywhere in the substrate, and then they start growing, to larger size. Eventually, they meet together, form this grain boundary, which is the source of this electron scatter, makes this high resistance. So the question is, can you really control this grain boundary? Without having grain boundary, can you merge them together? This is an idea. So here, this is an example. If you use this very polished sample, where you can minimize the number of nucleation seed, and you see the initial at the initial growth stage, the graphene flake is quite large. Whereas if you don't do that, the size of the graphene flakes are very small. So that means when you merge them together in a large area, the grain boundary effect is more dominant in this case. So this actually this gives a lesson that, okay, if you can control one nucleation seed, and you can enlarge that onto a large area, of course that will be very ideal, but that takes forever. So it's like a day or so. So you don't like that idea. So in our case, okay, so the question, when we decide to work with, we actually had the question, how can we observe this grain boundary easily without even using sophisticated TEM, for instance? Here, TEM, you can see the presence of this grain boundary easily because of this atomic resolution. But when you look at by optical microscope, which is the easy way, you cannot see it, right? So our question first was how to observe this grain boundary using just a simple optical microscope. So so this is one example, just using optical microscope, you can still observe the presence of these grain boundary lines. So how to do that? In our case, we simply create some very simple method. Here we have this copper substrate. We have a graphene on it. And then you irradiate this substrate with radicals, oxygen radicals. And interestingly, these oxygen radicals penetrate through this graphene on top and then oxidize the underneath copper. So this copper has a sort of volume expansion due to oxidation. This is actually what we can observe through optical microscope. So idea is very simple, but the consequence of that is we can observe grain boundary using just a simple optical microscope. So we have done this one several years ago, and we confirmed this is really what happens. Now, once you have this idea, for instance, this is one good example you can play with. you can simply wrap this graphene on any kind of pencil, and you create this bending. Of course, this bending will generate cracks of the graphene, and if you reduce the diameter of the pencil and the bending increases further, eventually the crack occur. And then you can see the crack propagates, and at some point at the grain boundary, the crack stops, and then change the direction and then propagate. So this is actually, crack propagation stops at the grain boundary, which can be visualized very easily using this graphene. Three-dimensional case is not easy to observe, but just a simple tool that we invented actually allow us to observe these kind of things. And another thing that we are interested in, of course, is electrical property. So by changing the simply gross temperature, this is a polycrystal graphene, and we can by increasing temperature, we can increase the size of the grain and then reduce this grain boundary. And actually, by combining all this, here is a summary. Sheet resistance has a graphene grain size, and then this sheet resistance decreases in increasing this grain size, which follows this simple scaling behavior. And the pure resistance of the single grain is 230, which is still large because CVD grown graphene still will have point effects in the grain, even though you don't have this grain size. Anyway, the same idea can be also applied for any kind of TMD materials. In this case, molybdenum diselenide on sapphire. We can simply again oxidize a sample and observe this kind of grain boundary. So the idea works for any kind of material. Okay, so from application point of view, is this grain boundary really best thing? And we thought about this one, and then actually the grain boundary is very sensitive to environmental gases, which can be used as some kind of gas sensor. So you can control it, and actually you can manipulate this grain boundary with many different chemicals that shows different electrical conductivity reactions. So at some point, if you like to use it, this will be certainly an advantage. So this is one good example. You can actually decorate this grain boundary with different radicals, different amounts. You can see there is systematic changes. So you can actually use this kind of characteristics as a sort of application for sensors. Now, of course, at some point we need to determine this the resistance at the grain boundary precisely. In this case, we have to make this a multi-electrode near the grain boundary. And between number 12 and 13, we do have this grain boundary. So you can see at the grain boundary, the resistance is very high. So certainly, although this grain boundary is influenced by different chemicals, in any case, even though you try to remove these chemicals, the resistance is still high. So we confirm that this resistance, the intrinsic properties of the grain boundary. Now, coming back to this issue, whether we can grow this large area graphene without grain boundary. So our approach, of course, if you start with a single nucleation seed, of course, that will be very ideal, but which is very impractical. So we rather decide to choose with multiple nucleation seed, and then have a quick growth, and then remove this grain boundary. So our idea was very simple. Here we have two graphene flakes with two different nucleation seed and in different orientation. You can see, and then when they meet together, so we form this grain boundary, and this grain boundary can be observed by using our simply oxidation technique. You see there is a grain boundary in the middle, in general. And when you have two graphene flakes in the same orientation like this, they meet together, and then you see there's no grain boundary. So the question is, how to align them together? This is the question. So There are several examples to demonstrate this concept. Using this Raman spectroscopy, you can identify the formation of this grain boundary. I'm not going to go into details, but because when these graphene are stacking, we can stack these graphenes together. And there is heavy stacking, when there is a twisted, and there's a monolayer. You see this G to 2D band intensity ratio changes very consistently. We can take advantage of it and then have a mapping, and you can see contrast ratio. If there is a contrast ratio, this means it is not a single grain, it is a multi-grain. So we can actually prove it. So when these are two graphene flakes in the same orientation, you see there's no such grain boundary. So you can also identify this using this confocal Raman mapping. Now, when we try to publish the paper, the reviewer, keep arguing, can you really prove this? There's really no grain boundary in atomic scale. So we actually did a series of experiments. This is one good example using STM. And you can see on this line, there is no boundary. The crystal structure is well aligned. So we prove it. Now, question of a large area. Now, this is a sort of centimeter scale. When we follow this principle, here with this, again, this is another method of observing this, the grain boundary existence by using this liquid crystal droplet. You can simply drop the liquid crystal on the surface. And if you have a different orientation, liquid crystal aligned in different orientation. So you can actually see, different orientation. This is one good example, polycrystalline graphene. So it shows different contrast. That means, because of different orientations of this liquid crystal on different orientation of graphene, you can see the difference. Whereas for the monocrystalline graphene, we don't see that. So this is one good example, monocrystalline graphene. And polycrystalline graphene, you can see there's different patches. Now, of course, the electrical conductivity and sheet resistance changes as well. You can see the monocrystalline graphene improves this sheet resistance almost twice, as well as also the mobility. Now, our next question is, can we really fabricate this bilayer graphene, which is AB stacking order, which is technically very important for switching device application? We need to have AB stacking large area. So because we are able to get the monocrystalline large area graphene, we can actually overlap them together and then get the bilayer, AB stack bilayer. This is the dry transfer process. So we don't associate any dirty PMMA in between this interlayer. So we have a very high quality bilayer. And once you have this bilayer, we can simply fabricate the device. And then you can see the threshold voltage consistently varies. That means we do open the band gap with this AB stacking order. So this one clearly indicates that our quality of AB stack bilayer graphene is very good. But still, it's a very sensitive issue whether you have really truly AB stacking order. So you have to go something more seriously. So in this case, we do observe this quantum Hall effect. You can see a clear Landau level discretized, and then you can simply identify them. And if you simply twist by even less than 1 degree, you can see clearly different Landau level up here. So this indicates our method works, even electronic point of view. You can see these clear Landau patterns different way. Now, of course, you can then try to make millions of devices. In our case, so we have several hundred devices on the same wafer, and we try to calculate this mobility in each device. You see they are quite uniform. They are mostly from this AB stacking order, although like 5% is still non-AB stacking order. This is artificially created bilayer, single crystal bilayer, but I mean, it perfectly works. Now, when you come to application, because I have been working with graphene and nanotubes, many people ask which material is better. I think most of the industry people, they always wonder, oh, which material do I have to work with, right? So the question is like, who's stronger, Spider-Man or Superman? You cannot tell much, right? I think the reality is the same thing. We cannot tell much. My point is like this. If you have two materials, of course, one is machine gun, the other one is shotgun. Now, depending on how to manipulate, of course, one can be even more efficient than the other, depending on how you approach, right? But if you have both, of course, you certainly have variables, you can be stronger. So Arnold Schwarzenegger, he's now become much more stronger with two weapons, okay? We have two weapons. As a material scientist, I think this is very important. So the question is how to manipulate, how to work with it. So I'll give you two examples, one for electronics application, the other one with energy storage. So I hope you understand what's going on. So one issue that we are facing in Korea is the future electronics, which can be wearable device. That means it has to be flexible, it has to be stretchable, right? And the stretchable requirement by the industry is like a 20% of stretchability at least. But all these materials, you cannot have this 20% of stretchability. So question is how to achieve it. For simple transistor, we have source and drain metal. They are also inorganic, so they are not stretchable. And we have also silicon channel. They are also inorganic, so it's not stretchable. And we have oxide. So they are not stretchable either. So none of them are stretchable. If you make them very thin, they can be flexible to some degree. Fine. But that's not what we eventually want, okay? We need a stretchability. So we come up with an idea, okay, we can simply replace this metal by graphene electrode because it's highly conductive, and we can use a semiconducting carbon nanotube as channel material, and then we can demonstrate it. Now, so with this one, we first try to fabricate all these devices on PET substrate and simply try to bend. So it works actually. The device works perfectly, even with a less heat state. I'm not going to discuss details, but this all carbon electronics works with all reasonable numbers of the device characteristics. Still, I didn't mention this backgate oxide, which is a silicon oxide still. And this is usually in our laboratory we use 300 nanometer, and it cannot be stretchable at all. So I had a little cheating on this. So we come up with how can we play with this gate oxide? Of course, one can introduce some like polymer. Polymer is an insulator, but most of the polymer shows leakage current, high leakage current. So for highly sophisticated device, you cannot use it. Then we come up with what can we do with this one, and then we thought about okay, can you use really inorganic oxide? So in this case, of course, nowadays we can have thickness control this aluminum oxide or silicon oxide using this ALD method, atomic layer deposition method, but still they are inorganic. So, but if you make some kind of wrinkle structure, or like a cotton, you have this cotton, and even though you move it back and forth, nothing happens actually. So if you have originally implemented this wrinkle structure in the oxide, they should be okay. So we actually created two-dimensional wrinkles, aluminum oxide wrinkles, and then they can be stretchable. So this is a method. We have a copper foil, and we simply deposit aluminum oxide using ALD. And then we deposit PMMA on top of it and remove this copper. And then we transfer this onto the desired substrate. And you can see they are wrinkle structure. And then we are wondering still what happens to this. So we did some simulation. You can see when you try to stretch the inner part up to 20%, they are fragmented. The red color means they are fragmented, but the bottom still they maintain this blue color. So the inner part has a high strain, but the outer side is still maintained okay. So up to 20%, we are quite sure this one should work. In fact, that's actually what happened. All the device characteristics, it works perfectly. And one thing nice is with this approach, even the subthreshold is really close to the ideal value of 60 milli-electron volt per deck. So this is a very high performance device. And you can simply stretch them, and you see the device still looks fine. And of course, there is some delicate issue. How much time do I have? Oh, okay, so I have enough time. And there is some delicate issue when you create this wrinkle structure, because if you look at the device, we have some kind of air gap. This is quite problematic. If you draw this equivalent circuit, we do have this air gap capacitance, which decreases the total capacitance. Actually, if you decrease the total capacitance of the device, the on current actually increases. So there is some problem, but the advantage of this air gap, we can significantly, although the on current is slightly decreased here, this leakage current is completely prevented. So even better than the regular device. So this is an advantage. When you consider this on current, of course, this capacitance decrease actually decreases the on current, but mobility is actually canceled out by this denominator capacitance. So the mobility is quite independent of this air gap. So this is quite lucky, because then we can maintain a high mobility as well. And then also, because we use a CNT as a channel material, there is another advantage that we have this high substrate, very low subthreshold thing because of this special localized field emission that controls these carriers very efficiently. So this one has certainly some advantages. Now, when you really stretch them and then you see how the device characteristics work, you see up to 20%. They work perfectly. And if you test this fatigue test, just simply repeating this on many, many times, still they're okay. So it's quite robust. So we are quite happy with these results. And you can simply transfer this whole device onto any kind of desired stretchable material, and you can see they are all fine. Now, let me, for the last 5 minutes, I can focus on this energy storage. And I don't have to emphasize the importance of this energy storage. I think all you are familiar with this one. But one thing I like to, whenever I come to this South Asian country, like Vietnam or China, India, I see some less here, at least at Pune and Bangalore. A lot of motorbikes. And this motorbikes really bug me a lot because it's quite noisy and also smelly. You see the air pollution is very serious. I think mostly caused by this motorbike. So can you really replace these motorbikes by electrical bikes? And actually in Beijing, there is a KFC run by an American company. They all use electrical bike. They take this battery, lithium-ion battery, because it takes time to store, to charge. They take that out and then put it in the bike and then come back and put it back to charge. So they have many lithium-ion batteries, and then they can be charged in a separate way. But if you can, of course, charge it immediately, that would be very nice, right? So, so our target is to create some kind of storage device. Of course, we have two different approaches. One is simply the conventional battery approach The other one is capacitor approach. Now, as you all know, battery has high energy density, whereas very poor power density. I mean, it takes time to charge, right? For supercapacitor, we have a very low energy density, but very high power density. So if you can, either you improve this power density from battery or energy density from capacitor. That will be, you can choose, it's up to you. Many people are working on different research direction. My choice is this capacitor because, well, I believe is that we have more freedom. Because the battery for the last 50 years, they increased the energy density only by a factor of 2. So they are already saturated because of mostly cathode material. So, but when you work with this material, there is always a trade-off phenomena. When you try to increase the porosity, energy density is good, but the power density becomes poor, things like this. So it's always mixed up. So you have to really play hard on this. So, and there is energy density versus power density and volumetric density versus gravimetric density. Either you increase this volumetric density or then you have to sacrifice this gravimetric density. And we don't want to lose both because we need a volume, we need a mass. So if you look at this, again, the characteristics for energy storage for CNT and graphene, they are very similar. Mostly they are creating the micropores. And this actually is good, but this ion diffusion is a big hurdle. So unless you pay attention to this ion diffusion, you cannot make a good performance. This is why Professor Sanchez is making this multiporous structure. I think that's also a very good fit for this application. So question is, when all these nanotubes and graphene powder, we're talking about powder, when we make this film again, they all aggregated and then they kill everything. So ion cannot be diffused at all. So, but when you look at this, this electrode structure, this electrode has to have some kind of porosity to allow ion diffusion, and also has to have some microstructures to store. So you have to have both multipole structure. Now, how to optimize the ratio between these two is the key. So, and again, when you work with the graphene, many people think, oh, graphene is great material. I mean, this Manchester group also proposed this supercapacitor. But you have to pay attention to, because this is just one simple example. We have this copper, we have graphene, 1 layer, 2 layer, 3 layer like this. And when you work with a lithium foil, lithium actually try to attack this copper and then damage this copper. But if you have a graphene on it, it will be blocked. Of course, graphene has some defects, so you cannot completely block. So, but if you increase the number of layers, actually you see the reaction decreases. That means graphene etching is, or this can be minimized up to, by using CVD sample up to 6 layer, you can completely block this reaction. So this is a lesson where this ion diffusion really cannot occur through this graphene layer. So if you stack them and then you try to have this ion diffusion, you cannot. So our idea, of course, we like to take advantage of both material. So we can simply mix nanotubes and graphene oxide powder together. But there's a trick. Graphene oxide, GO, can be dissolved well in water because it's this negative charged ion. And then nanotube itself is hydrophobic and they cannot be dissolved in water. So you need some kind of surfactant. In this case, the trick is to use this CTAP, which is positively charged head groups. So the tail part interacts with nanotubes, and it's all the positively head group is located outside. So when they mix them together in water, they form this electrostatic interaction and the microemulsion form, okay? Amazingly, we have this kind of structure. Okay, we had one more treatment. Even though you have this three-dimensional building blocks, because of this graphene that blocks this ion diffusion, we have to create some kind of pores, small pores, by using this KOH activation. The process is very simple, so we can optimize this. So even ion, of course, can go through this channel very easily, but even through this graphene layer as well. So this is the key. So you can actually, by looking at the SEM on top, you cannot see much. It's just a random network of nanotubes. But if you look at sideways, by cutting, you see nanotubes are aligned like this one. Of course, this can be created by, during this cutting. So you have to argue whether this is really aligned or not. Anyway, so we have two questions. One, when they got stacked together by this electrostatic interaction, they simply stack them back again. And another question is, are these nanotubes are really aligned perpendicular to graphene? So when you look at this XLD, with this activated graphene nanotubes, that is blue line, you see there's no peak. That means they are not aggregated back, which is a good sign. And how to prove this alignment of nanotubes? In this case, we simply use the polarized Raman. 2 minutes, okay. So use this polarized Raman. You shine the light with a polarizer, and then when the light parallel to this nanotube, they penetrate, and we see this, when you rotate this polarizer, you can see the intensity of this G-band changes. That means the nanotubes are really aligned perpendicular. So, but if you use just a regular surfactant like SDS, which is negatively charged, you don't see that effect at all. So nanotubes are completely randomly aligned. So you see the big changes in the G-band intensity as you change this polarizing angle. So this is an evidence of this nanotubes alignment. And one thing that I like to emphasize is this density of the sample. The density, in this case, 1 gram per cubic centimeter, which is very high, even though this is highly porous. So this is the key. Then you can have a volumetric, gravimetric, both values very high. Since I don't have time, one thing I like to emphasize, we have a certain amount of micropores, certain amount of major pores. This is very important. We optimize this structure, very important. And conductivity also very high still. And then ion relaxation or ion diffusion can be represented by this value. So our sample actually has very low. That means ion diffusion is fast. Anyway, so I'm not going to go details on this, but if you look at this Ragon plot, when you make the capacitor or battery, this is the one you need to look at. So energy density versus power density. Now we see our red color. Over the wide range of this power density, the material, do not degrade much. So energy density is kept a very high value. So this is nearly 100 watt-hour per kilogram. The best LIB lithium-ion battery shows less than 200. So this is already, we are in the same order. And it's very good. And not only, this is a gravimetric. If you look at the volumetric, still we maintain a high value. So the reason is because we have a very high mass density instead of having this highly porous structure. So this is the key. So you see our value is here. So I think we are working on now with a company to commercialize this one. Then we found out one problem that company suggested. All this energy storage work, if you have a very thin film, it works because of this diffusion. If you increase the thickness, then ion diffusion is limited, then you have this performance sacrifice. Now, company requires 100 micrometer, whereas in our case, up to 20 micrometer perfect. But if you increase up to over 20 micrometer, then you have problem. So we are now working together how to overcome this difficulty. So the service is not the end. So it's still ongoing, okay? But it's a very interesting scientific and also application. I think both are very good. Anyway, so I'd like to conclude my talk. still a lot more, depending on how you use it, okay? So the message, we have a lot of people here, and we have to go further. At the moment, we cannot say much, but I'm sure this new technology will impact our society in a very profound way in the future. This is what we are working on at the moment. Thank you for your attention.
Young Hee Lee, thank you very much for telling us right from the very basics of graphene to the supercapacitor applications, very fascinating results. I again apologize that we are about half an hour late, but again I'll invite only one question. Yes, Ramgopal Rao. Since you are the award winners,
that's right.
You have the privilege of asking this.
That was an interesting talk. So, in fact, when I looked at your graphene device structure, you are proposing to use graphene film for the substrate kind of a thing.
That's right.
But we have seen that graphene, when you flex the graphene, it shows a huge change in conductivity. So now if you have a flexible electronics with graphene as a substrate, and every time you flex it, if the device behaves differently, you can never build any circuits out of that, I thought.
Well, I mean, that's a tricky part, okay? In our case, when we use graphene as an electrode, we actually overlap CNTs together. This is a tricky part. So even though graphene cannot tolerate this high stretchability, CNT, the remaining CNT, still acts as a electrode, and they are still okay. So again, the graphene, when we make this transfer, some degree they are wrinkled, so they can tolerate some strain as well. So I think combining all this together, this is sort of this consequence. So you cannot, if you just add up this CNTs on the channel area, there may be a problem, but we don't have to, right? So it's a trick.
All right, I think I'll take this opportunity to close this session, thanking both the speakers once again. And I appreciate your patience, even though we are half an hour late, and we'll close this. Thank you very much once again.
Thank you.
Before we all head towards the lunch, kindly stay back. I'll have to make an announcement because you need to find your way where exactly the lunch is, so kindly stay back. I would request Professor Sood to give a memento to our esteemed speaker, Mr. Lee. Thank you very much.